So far, we learned that if we have a continuous function and the region that it's bounded to is something like a sector or circular shape, for example, theta is bounded between alpha and beta, or in general, theta 1 and theta 2, and your R is bounded between R sub 1 theta and R sub 2 theta, or between two fixed values, it doesn't matter. Then you can convert your double integral from Cartesian plane into coordinate plane and take the double integral. So wherever you see x, you're going to use R cosine theta. Wherever you see y, you're going to use R sine theta. And remember that dA becomes R dr d theta. This is the important part that we usually emphasize for students when they are completing their homework, learning the materials, or preparing for the exam itself. In this question, find the volume of the solid bounded by the plane z equal to 0 and the paraboloid z equals to 1 minus x squared minus y squared. Basically, if you set z values equal to each other, it means that you plug in 0 for the second equation, we get x squared plus y squared equals to 1. So this is 0, which is 1 minus x squared minus y squared. You can bring these two to the other side. You get positive signs, and so x squared plus y squared becomes 1. But what's the meaning of that? This means that the plane intersects the paraboloid in the circle x squared plus y squared equals to 1. This is basically your unit circle. So the solid lies under the paraboloid and above the circular disk d given by x squared plus y squared less than or equals to 1 in this case. So as you can see, the difference between a circle is just the boundary points, but when you're talking about a disk, it includes interior points and the boundary points as well. We can take a look at the visualization here. So first of all, x squared plus y squared is equal to 1, which is this circle, as you can see, in the plane xy. And then you have the paraboloid z, which is 1 minus x squared minus y squared. So if we graph this as well, as you can see, it opens downward. And we look at the intersection between this 3D surface and the circle in xy plane. In polar coordinates, we can rewrite d in the following form. X is r cosine theta, y is r sine theta. So if you plug those in to the inequality, you get x squared, which is r squared cosine squared, plus y squared, which is r squared sine squared, and this simplifies to r squared. So it says, hey, your r squared is less than or equals to 1. Basically, if you take the square root, you get r less than equals to 1. But please note that your r is between 0 and 1. Well, we're not worried too much because r has constant boundaries. Now for theta itself, theta is bounded between 0 and 2 pi because it's a full circle. The object starts at positive part of x-axis and it has a complete rotation, which is 2 pi. So we found the boundaries for our r and theta, and we are ready to move on to calculate this volume. Since 1 minus x squared minus y squared can be rewritten in polar form using x equals to r cosine theta, y equals to r sine theta, this is 1, minus r squared cosine squared, this is your x to the second power, r cosine theta, minus y squared, which is minus r squared sine squared. This is y squared, which is r squared sine squared, and this is coming from the definition of polar coordinates. At the same time, we know that r squared cosine squared plus r squared sine squared is equal to r squared. So basically, if you factor out the negative sign here, you get 1 minus r squared cosine squared plus sine squared, which is 1 minus r squared. So basically, we just factor out r squared here. This is 1 minus r squared in parentheses cosine squared theta plus sine squared theta, and this is 1. So that's how you end up with 1 minus r squared. Now the volume is the double integral of 1 minus x squared minus y squared dA, which is 1 minus r squared. We just did the simplification up there. And for dA, we have r, dr, d theta, and r ranges between 0 and 1, as you saw just right here. And theta is bounded between 0 to 2 pi. Again, be careful when you're writing dA. dA is r dr d theta. Take a look at the proof if you need to take a look at the short proof or longer version to feel more comfortable about these kinds of proofs. This guy can be written as, well, here you can separate d theta and r dr 1 minus r squared. These two are not connected together. There is no additional subtraction between r and theta. So we can basically separate this into two easy integrals. The integral of d theta and the integral of r minus r cubed dr. In calculating the integral, we're basically using the integral of u to the n du, which is u to n plus 1, divided by n plus 1 plus c. And since you have definite integral, c disappears. So remember that here I distributed r into parentheses. That's how we get r minus r cubed. Now for the integral itself, the integral of d theta is theta you just plug in 2 pi minus 0, you get 2 pi back. And then for the integral of r, this is r squared divided by 2 minus the integral of r cubed, which is r to the 4th divided by 4. And r is bounded between 0 and 1. So when you plug in 1, you get a half minus a 4th multiplied by 2 pi, which is pi divided by 2. So again, here you have a disk. The radius shrinking to 0 and expanding to 1. So that's why r is between 0 and 1. And as you can see, since you have a full rotation, this object from positive part of x-axis starts rotating and it goes back to the original point that it was. That's how you have theta bounded between 0 to 2 pi and r as the radius show the shrinkage to the origin, and in maximum form it expands to radius equals to 1.